In the last class, we have discussed bisection method, how to apply bisection method to find the solution of the nonlinear equation. In this section, we'll find out error round for the bisection method. So we are going to start a theorem. This theorem is about to find out rate of convergence of bisection method. Suppose that f is belonging to CAB. What does it mean? It means f and f dash is continuous inside the interval AB. F and f dash is continuous in AB. Okay, f belonging to CAB, and f of A, f of B is less than 0, then the bisection method generate a sequence xn n equal to 1 to infinity, approximating a 0 alpha of f with xn minus alpha is less than equal to b minus a upon 2 raised to power n when n is greater than equal to 1. Okay, so let's understand the statement. Suppose f is a function that is continuous and differentiable inside the interval AB, and multiplication of the function f of A and f of B is less than 0. That means f of A and f of B are of opposite sign. Okay, so the bisection method generate a sequence. Then if we apply, in this condition, if we apply bisection method, then it will generate a sequence xn that is approximating the root of the function with mod of xn minus alpha is less than equal to b minus a upon 2 raised to power n. In the last class, we have discussed the length of the interval that is less than equal to b minus a 2 raised to power n after n steps. Okay, so it is similar kind of proof as we have already done in the previous class, but let's do it again. So xn minus alpha is the exact root. Xn is the nth approximation to alpha. So xn is what? That is the nth approximation to alpha. Okay, so let's do the proof. Recall bisection method. What is bisection method? In this method, this interval is given to you AB, f of A, f of B, f of A, f of B is already less than 0. That means either f of A is negative or f of B is positive or vice versa. Okay, so what we do in this case, when f of A, f of B is negative, that means our root is lying inside the interval AB. Okay, f of A, when f of A, f of B is less than 0, this implies that a root is lying in the interval AB. Okay, so what we do, first we'll bisect this interval AB. So bisect the interval AB. Let x1 is the midpoint of AB, so x1 equal to what? A plus B upon 2. Okay, so the root is lying either in the interval. So what we have done here, we have divided this interval AB into two subintervals. Okay, so we are taking I0, it is the first interval. Okay, I0. And x1 is what? That is the midpoint of AB. So we got two intervals. Let us suppose AX1 and X1B are two intervals. Either AX1 or X1B contain the interval. So root is lying either in AX1 or X1B. How we can make it sure? How we can make it sure? Either so this implies that either f of a into f of x1 is less than 0 or f of x1 f of b less than 0. Any one of the condition will be there. Let ax1 contained the root. That means root is on the left side of x1. So taking a1 equal to a and b1 equal to x1. So we form a new interval, that is what? Ax1. We have given the name a2 as a1, x1 as b1. Okay. So what is the length of? Let us suppose the new interval is length of the new interval a1 b1 equal to b1 minus a1. It is half of the interval ab, so we can write it b minus a upon 2. Okay, b minus a upon 2. So we can write it length of I1. This I1 is what? Where I1 is A1 B1. It is new interval. This I1 is contained in I0. Obviously. Now we will again subdivide this interval. We'll again subdivide this interval A1 B1 into equal subparts. Let us suppose the new point is what? X2. So root is lying either in this interval or in this interval. So again subdivide or bisect. I should use a proper word, that is bisect. Bisect the interval A1 B1. Okay, so what we'll get? Suppose x2 is the midpoint of A1 B1. Then we can write it x2 as A1 plus B1 upon 2, and the interval we formed A1 x2 and x2 B1. Okay, so we got these two intervals. Okay, so either f of a1 f of x2 is less than 0 or f of x2 f of b1 is less than 0. Let the second case is our case, f of x2 f of b1 is less than 0. So the new interval formed is I2 x2b. Will give this interval name, will give the name to the endpoint of this interval as a2 as x2 and b2 as b1. Okay. So the new interval is what? I2 equal to a2 b2, and length of I2 is b2 minus a2 or it is half of the interval I1, this is I1 upon 2, or equal to I naught upon 2 square, because I1 is what? I1 equal to I naught upon 2, that's why. Continue this process, continue this process. We'll get interval In. In is what? An, Bn, and length of In will be what? Bn minus An, or it can be written as I naught upon 2 raised to power n. Okay, so length of In is equal to I naught upon 2 raised to power n. Okay, so in this case An and Bn is what? An and Bn is a very, very small interval. After an step we are getting this interval, and this interval In contained the root. In contained the root. Okay, let alpha. Okay, so maybe this alpha could be anywhere inside this interval, maybe here or here. Let us suppose alpha is somewhere here, and suppose xn is the midpoint of the interval In. Okay, so xn is what? Somewhere. This is your xn. Xn is midpoint of A and Bn. Okay, and alpha is what? Alpha is anywhere different from the midpoint, and it could be midpoint also, because whenever the midpoint is approaching toward alpha. So if we write here this xn minus alpha. Xn minus alpha is what? That is lesser than the length of the interval In. We can write it Bn minus An. If xn and alpha, it will be what? It will be less than equal to length of the interval In, or we can write it as I naught upon 2 raised to power n. Okay, so we can write it here xn minus alpha is less than equal to b minus a upon 2 raised to power n. So this is called upper bound for the xn minus alpha. Okay, so we can write it xn minus alpha is less than equal to b minus a. This implies that the sequence xn converges to alpha with rate of convergence order of 1 upon 2 raised to power n. That is xn equal to alpha plus order of 1 by 2n, because in, like, if you see from here, from the starting, what we have done, we have divided the whole interval AB into half parts, that we got A1 B1, and then we divided A1 B1 into again by A1 B1 again we bisect into 2 sub intervals, we got A2 B2, and continue this process we are getting A and Bn. This A and Bn is what? That is a very small interval, it is containing the root. Then the difference, then the length of the interval is what? I naught upon 2 raised to power n. And xn minus alpha is what? Their 2 point alpha is the exact root, and xn is what? That is the midpoint. Then the difference between xn minus alpha, that will be definitely less than equal to the length of the interval a and bn. And length of the interval is what? I naught upon 2 raised to power n. So in that case, we can write it as xn minus alpha is less than equal to b minus 2 raised to power n. This is the upper bound error. So from here we can say that if this right hand side term is 0, then we can say xn is equivalent to alpha. So in that case we can say as n is approaching infinity, then the sequence xn converging to alpha with rate of convergence is what? 1 by 2n, because in every step we are dividing the interval in by half. Okay, so that means xn is equal to what? Alpha exact root with order of convergence 1 upon 2 raised to power n. This is also called rate of convergence of 1 by of the bisection method. Okay, so this proof is done, that we have to prove. Next is number of iteration in bisection method. Number of iteration in bisection method. Number of iteration in bisection method. This error bound help us to find out number of iteration in bisection method in advance. Suppose we have done one question in the last class. There we got result or we got root within 10 raised to power minus 1 in 4 iterations. Okay, in some question the number of iteration may increase, it may be 10, 100, 200. If we know these number of iteration in advance, then it will be very, very helpful. Okay, so in this bisection method we have the facility that we can compute number of iteration in advance. Okay, so how to do that? We have already proved, like xn minus alpha is less than equal to b minus a upon 2n 2 raised to power n, that we have already shown here. Okay, and what we want that the obtained result should be accurate up to n decimal digit. Okay, so for that, let us suppose epsilon is given to you. So we can write it xn minus alpha is less than equal to b minus a upon 2 raised to power n. This is what? This is the upper bound for the error. Then epsilon is what? We want our result or xn accurate to n decimal places. So in that case, that xn, whenever xn plus 1 minus xn is less than epsilon, then we can stop our iteration. So that's why what we are doing here, xn minus alpha, or we can write it as we have done in the previous class, xn plus 1 minus xn is less than equal to epsilon, that we have done in the previous class. Okay, whenever we are getting that xn plus 1 minus xn is less than epsilon, we stop our iteration. Okay, so this xn is approaching toward the alpha, that's why we are getting xn minus alpha is less than equal to b minus a upon 2 raised to power n. So we can replace this condition by xn plus 1 minus xn is less than equal to b minus a upon 2 raised to power n. So b minus a upon 2 raised to power n is less than equal to epsilon. Now we can write here in logarithmic form b minus a minus n log 2 is less than equal to epsilon, where as n is what? That is the number of iteration, because this we got in nth iteration. And log 2 get the value of n. N is greater than equal to log of b minus a minus log of epsilon upon log 2. It could be base 10 or natural, it depends, you can take any. Okay, now. So this is the result for number of iteration required to get desired accuracy in bisection method. Okay, so log of b minus a minus b and a are what? These are the endpoint of the interval in which the root is lying. Epsilon is the tolerance and log 2 that you can compute. Okay. There is one note about this statement. I should write in this theorem. about this theorem, if we say xn minus alpha is less than equal to b minus a upon 2 raised to power n, then in this case we can write a note this theorem gives only the bound for approximation error, and the bound might be quite conservative. That means it is not saying like from this statement, from this theorem we cannot say that is the exact value of the error is coming out to be this. We are getting only the upper bound of the error. Okay, we are not getting exact value of the error bound. Okay, so this is bisection method. There is some drawback of bisection method. Just a minute. Drawbacks. Right. Of bisection method, or we can say BM method. One, this method is slow. Second, if the function we are having fx equal to x square, if we draw the graph, in this case it is only touches the x-axis. At x equal to 0, this function x equal to 0 is the root of this equation, x square equal to 0. Okay, so it touches the x-axis, then we do not have a and b such that f of a, f of b is less than 0. In this case, we are not able to find any a and b such that this condition holds. So for this question, VM will not work. Bisection method will not work. Okay, but x is root of fx equal to 0. So VM method cannot be applied. Okay. Third point, suppose fx equal to 1 upon x. In this case, f of a, f of b is less than 0. Suppose a equal to 1 and b equal to minus 1. So in that case, what we are getting, f of 1, f of minus 1, it is coming out to be negative. Minus 1 less than 0. X function f of x is not continuous at x equal to 0. Okay, so IVT cannot apply. Not apply. So just keep in mind whenever you are applying VM method, so in order to apply intermediate value theorem, function should be continuous. Sometimes you are getting only the point a and b such that f of a, f of b is less than 0. That is not only the condition. Function continuity is also important. Okay, so x equal to, due to x equal to 0, function is not continuous at x equal to 0. So obviously it is not having root at inside the interval 1 to -1, but only by this condition, and you are not knowing the continuity, you are not knowing about the continuity of the function, then you can say okay, there is a root lying between 1 to -1, but it is not -1 to 1, but it is not the case. So with this condition f of b is less than 0, continuity is also important. Okay. So the bisection method is over here. Next method that we are going to discuss, that is what? Fixed point method. Fixed point method. Fixed point method, it is also used to find out the solution of nonlinear equation. So before going to discuss about this method, we must know what is fixed point. Fixed point. What is fixed point? A point alpha is said to be fixed point of a function f(x) if f of alpha equal to alpha. That means the numerator, that means the input and output is same. Then we'll say alpha is the fixed point of the function f(x). For example, f of x equal to x square. What is the fixed point of this function? If we check f of 1, it is coming out to be what? 1. F of -1, the function value is 1. F of 0, it is 0. F of 2, it is 4. F of -2, again 4. So what are the fixed points? Fixed point whenever the whenever the input and output are same. So this is fixed point. Fixed point. Why? Because this input and output both are same. -1 is not equal to +1, -1 is not equal to +1. So here alpha is not same, not a fixed point. Both are same, 0 is a fixed point. Okay, here no. So 2 and -2 are not fixed points. So there are only two fixed points of a function. So f(x) equal to x square have two fixed points. Those are 1 and 0. Okay, so fixed point of a function is what? Where the input and output are same, or function is having same value as the input. Okay, one more example we can take. f(x) equal to x square minus 2. What are the fixed point of this in this case? Here f of 1 equal to what? 1 minus 2 minus 1. Not a fixed point. 1 is not a fixed point. F of 0 minus 2. No. F of minus 1 minus 1. Minus 1 is a fixed point. F of 2 equal to 2. F of minus 2 equal to 2. Also here these both are same. 2 is a fixed point. Minus 2, no. Okay, so here minus 1 and 2 are the fixed point of the function fx. How to compute fixed point of a function? How to compute? So the best procedure is what? One is what? Like just put the value of the input and get the output. That is one procedure. Another procedure is what? Just put f of alpha equal to alpha. Put f of alpha equal to alpha. Get the value of alpha. That will be the fixed point. Okay. In this case, let f of alpha equal to alpha. So f of alpha equal to what? Alpha square minus 2 equal to alpha. So alpha square minus 2 equal to alpha. Alpha minus alpha plus 2 equal, minus 2 equal to 0. Get the value of alpha. From here, what is coming out to be? Alpha square minus 2 alpha plus alpha minus 2 equal to 0. Alpha minus 2, alpha plus 1 equal to 0. Get the value of alpha, that is minus 1 and 2. So minus 1 and 2 are the fixed point of the function f. Okay. So it is same to the minus 1 and 2. So if you want to compute fixed point of a function, just put fx equal to x or f alpha equal to alpha, get the value of x or alpha. That will be the fixed point. Okay. So in this section, why we have defined fixed point? In this chapter, we are discussing about the solution of nonlinear equation and also defining fixed point. So what we do in this chapter in this section, we will try to get a connection between the fixed point and solution of nonlinear equation or root finding problem. Okay. So what we do in this section, we will try to find a connection between root finding problem and fixed point. Okay, how we will do that? We will do it in two ways. One is, given a root finding problem, that means f of x equal to 0. We can define a function g with a fixed point alpha point at alpha in a number of ways. For example, what we do in this case, fx equal to 0, we can express in terms of a function gx such that alpha is the fixed point of the function, like g of x equal to x minus fx. Let us explain it with the help of some example. Suppose fx equal to, given to you, x square plus 2x minus 1 equal to 0. This is a problem. What you will do, you will modify this function in such a way such that x equal to some function of x. So if we want to compute x from fx, so what we can do, we can write it here as x square minus 1 upon 2. This is one procedure. From here we are computing the value of x. So what we can do, x square plus 2x minus 1 and compute x from here. That is x square minus 1 upon 2. Another way is what? Take x square plus 2x equal to 1. This is one procedure. Okay. Another procedure is what? This is one procedure. Second procedure is what? What we can do, we can take x common from here. X plus 2 equal to 1. Okay. So x equal to 1 upon 2 plus x. This is another procedure. Third procedure is what? We can write here x square plus 2x equal to 1. Okay, x square as 1 minus 2x. X equal to square root of 1 minus 2x. This is the third form. Okay, so what we do here, we'll write function fx equal to 0 and we'll define a function gx. What is gx in this case? This is your gx. Whatever you are getting in right hand side. This is your gx. This is your gx. So fx equal to 0 can be written as in term of x equal to gx. So what we have to do, we have to write, we have to compute x from fx in such a way that we can get some function of x that we named as gx. Okay, so there are infinitely many ways to express fx equal to 0 in term of x equal to gx. So this is the thing we have written here. Given a root finding problem fx equal to 0, we can define a function g with a fixed point at alpha in a number of ways. For example, gx equal to x minus fx. Okay, this is only one procedure. Otherwise, we have given this example fx equal to x square plus 2x minus 1. Compute x as you can compute. So here what we have done, we have computed x from here. So x square minus 1 upon 2. Okay. Except this, you can also compute x square minus 2x plus 2x minus 1 equal to 0. This is the fourth way. Just add one x here. Okay. So x equal to what? X square plus 3x minus 1. This is also your gx. So there are lot many ways to express fx equal to 0 in term of x equal to gx. And in what thing we are interested? We are interested in the fixed point of the function gx. Okay, why? Let me explain it. I told you here that fx can be expressed as x. We can write fx equal to 0, we can write here fx equal to 0 as gx equal to x minus fx. Okay, so let alpha is the root of fx. So f of alpha equal to 0, f of alpha equal to 0. Okay, so g of alpha will be what? From here it will be alpha minus f of alpha. What it implies? That f of alpha equal to alpha minus g alpha. From here, okay, I should write here, it is creating confusion. G of alpha equal to alpha. Alpha is what? Alpha is the, from here what we can say, alpha is the fixed point of g. If we are able to find out fixed point of g, then we can say that is the root of the equation fx equal to 0. Or we can write from here f of alpha equal to alpha minus g alpha. If alpha is the fixed point of g, then f of alpha will be what? that is alpha minus g alpha, because alpha is the fixed point, it is coming out to be 0. This implies that alpha, f of alpha equal to 0. This implies that alpha is the root of fx. So in this section we are interested to compute fixed point of the function g, that g we formed from fx equal to 0. Okay, so I think it should be clear in this chapter how we can connect fixed point with the root finding problem. Root finding problem, that means fx equal to 0 can be written in term of x equal to gx, and then we are interested to compute the fixed point of gx. If we are able to compute fixed point of the gx, then we can say it is the root of the function fx. So in the next section we will discuss about the gx function, what are the conditions required to follow via the fixed point iteration or gx function. Okay, thank you.